Hi there, this is Mrs. Often, and I'm here in this video going to be talking about isosceles and equilateral triangles. Our objectives in this video are twofold. We're going to be proving theorems about isosceles and equilateral triangles. Those theorems we will actually be proving in class, so be sure you get those in your notes if you miss out on class. And we're going to be applying properties of isosceles and equilateral triangles to solve problems including determining side lengths and angle measures. So let's get started. Two theorems about isosceles triangles that we'll be using. The first one is the isosceles triangle theorem, which in class we will abbreviate ITT. This says if two sides of a triangle are congruent, then the angles opposite the sides are congruent. So given AB congruent to AC, our conclusion is that B and C, those angles are congruent to each other. The converse of this is also true. We will abbreviate the converse of the isosceles triangle theorem as CITT. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So opposite to angle E is side DF. So if I'm given that E and F, those angles are congruent, I can say that DF is congruent to DE. Or as they've written it here, DE is congruent to DF. You may hear of these theorems called the base angles theorem and the converse of the base angles theorem. We have a couple of additional theorems that are not in your textbook. These are very helpful in drawing auxiliary lines to be able to prove the base angles theorem and the corollary to that. So every angle has exactly one bisector and every segment has exactly one midpoint. So we can use these to draw our auxiliary or helper lines. So we can draw ray AB as the bisector of angle A. We can draw M as the midpoint of AB. And then once we have the midpoint, we can use that to construct, for example, a perpendicular bisector of a segment. Now we've done this before. These theorems are actually proved using construction and the line postulates. Again, the isosceles triangle theorem is sometimes stated as base angles of an isosceles triangle are congruent, and that led to its name of the base angles theorem. So in our first example, we're going to find the measure of an angle. We're given that angle E has a measure of 22 degrees. We want to find the measure of angle F. Of course, we know because triangle DEF is isosceles, that angles D and F must be congruent. That is, they have the same measure. So my strategy is going to be pretty easy here. I have two unknowns. They're both the same value. X plus 22 equals 180. 2x is 158, and therefore x is 79. Therefore, the measure of angle F is also 79 degrees. In this case, things are a little bit more challenging because we have algebra involved. However, angle J and angle G are opposite to the congruent sides, and therefore they are congruent. Thus, the angle measures are equal to each other. We can write this equation, and we can solve using algebra. So x is equal to 22. That means that angle G is going to be 22 plus 44 degrees, or 66 degrees. Now, a couple of corollaries to the base angles theorem. We have equilateral triangle. If a triangle is equilateral, then it is equiangular. And hopefully you can see this as a corollary to the base angles theorem. I have a pair of congruent sides here at AB and AC. Therefore, B and C are congruent. But now also I have a pair of congruent sides at AC and BC. So that tells me A is congruent to B. And therefore A must also be congruent to C. All of my angles are therefore congruent. Taking the converse of this statement, I have E and F as congruent angles, therefore DE and DF are congruent sides, but I also have that D and E are congruent angles, therefore DF must be congruent to EF, and by extension, EF is also congruent to DE. So those are your corollaries. Pretty easy to prove as corollaries from the isosceles triangle theorem. Okay, so using properties of equilateral triangles, well, since the triangle is equiangular, every angle must have a measure of 60 degrees. We proved that back earlier in the unit. So triangle LKM is equilateral. If it's an equilateral triangle, it's equiangular. It must be 60 degrees in measure. Therefore, x is equal to 14. Now here, finding the value of JL, because this is an equiangular triangle, it is also equilateral. Therefore, 2t plus 1, 4t minus 8, the measures of JL and KL respectively, must be equal to each other. Solving this, we get t is 4.5, and the length of these sides, therefore, is 10. So JL is 10 and KL is also 10. Good way to verify this is 4 times 4.5 minus 8 is also 10. Okay, quick quiz here. Determining each angle measure. Angle R, well, R and Q must have equal measures because they are congruent angles. And so the measure of angle R is going to be equal to 28 degrees. And if R and Q are both 28 degrees, then angle P, so let's put this down, measure angle R equals measure angle Q equals 28 degrees. Therefore, the measure of angle P is going to be 180 minus 2 times 28, or 180 degrees minus 56 degrees, and that's going to be 124 degrees. To determine the value of x here, I can notice that this is also 52 degrees by the isosceles triangle theorem. By the linear pair theorem, 52 and this vertex angle must be supplementary, and therefore it has a measure of 128 degrees. That leaves the remaining 52 degrees to be divided between these two angles. Now, another way, if you had been paying close attention, this angle that I labeled as 52 is an exterior angle to my isosceles triangle here, so I could have gone about this more quickly. But I will again note that 180 minus 128 is 52 degrees. Therefore, x will be half of 52 degrees, and even Lola here knows the answer, that x is going to have a value of 26. So those are our answers here, and that brings this video to a close. I hope this has been helpful in improving your knowledge of isosceles and equilateral triangles and their properties. Have a great day.